Hello AP Chemistry and welcome to 17.2. Yep, still going. 17.2, and now we're going to talk a little bit about the terms buffer capacity and buffer range, right? So we're going to talk about it in the context of that previous problem, so we're going to skip some slides and we'll go back and do those, right? But in this buffer problem we talked about, right, we created two different buffers with the same exact pH. Yes, two buffers, same pH, we made them with different strategies, right? One had 0.2 moles and 0.2 moles, right? One had 0.1 mole versus 0.1 mole, right? Nope, I didn't circle that. Let's pretend I didn't circle that. Okay, so if we think about what that means in the terms of the language that we're talking about here, right? Buffer capacity, right, is the ability to neutralize, right? So if I had 0.2 moles of HA and A minus versus 0.1 moles of HA and A minus, which of those has a greater buffer capacity? Correct, this one, right? Yep, I was supposed to write that down here. 0.2 moles here, and 0.1 moles, right? But the point is, right, that it's a lesser capacity, right? This is basically the amount I have that can be neutralized, right? That can be used for neutralization, right? Higher buffer capacity has to do with the respective concentrations of HA and A minus in your solution, okay? And they don't have to be the same, right? So if you think back to that blood discussion in your guys' book, right? The blood's ability to buffer capacity is different for acids versus bases, right? So it doesn't have to be the same, but that's what capacity means, and that's how we would use that, right? Range, right? Thinking about what we've talked about previously, right? The range has to do with, right, basically it has to do with its pKa, yes? In that a buffer range is most ideal plus or minus 1 unit from pKa, right? So that means we need to know our pKa. So for example, chlorous acid, right? Chlorous acid has a pKa of 1.1 times 10 to the negative 2, right? So it has a Ka equals 1.1 times 10 to the negative 2, right? Which means that if I took the negative log of that, right, we would get something around 2, right? And which means that its buffer range would be somewhere in the range of 1 to 3, yes? The buffer range for chlorous acid is between 1 and 3. That's where it's most effective. Not that we can't make a buffer of different concentration, it's just less effective, right? Let's do boric acid, right? So boric acid is 5.8 times 10 to the negative 10, right? 5.8 times 10 to the negative 10, which means that its pKa actually sits somewhere around 10, right? Which means that, right, it would be most suited for something between 9 and 11, which means that boric acid, right, despite the name, actually makes a basic buffer. Yes? Makes sense? Okay, so now let's go back and do these practice problems that we skipped. So it says to calculate the pH of a buffer composed of that and that. So what do I need to know? Right. We need to know the respective K for benzoic acid, which is 6.3 times 10 to the negative 5, right? So, right, we'd like to calculate the pH of this buffer. So what I would prefer to do here, right, is that I would go ahead and I would start with my benzoic acid, right, where HA plus H2O gives us H3O plus A minus, right? And clearly I understand, and you understand, that benzoic acid, right, is our HA, right? A minus is the 8, right, the benzo 8, right? So 0.2 molar, that, right? And if I'm trying to find the pH, right, this is what I'm looking for, yes? So, and if we think back to that whole common ion effect, right, if I have A minus in a solution of HA dissociates less, right? To the point where we don't even need to consider the amount of dissociation, and we can just go ahead and do our math, right? So I can just go ahead and set this up as 6.3 times 10 to the negative 5th is equal to H3O plus times 0.2 over 0.12, and solve for my H3O plus, and then do the negative log of that, right? Obviously, alternatively, as long as you recognize that it's a buffer, right, so this question is a little bit, on the easy side where it literally says buffer, you could always use the Henderson-Hasselbalch equation, right? Remembering that base just means conjugate base, right? and acid means your weak acid, right? So you do just have to remember what that relationship is, right? Base is deprotonated and your acid is your protonated version. And you're more than welcome to use that. Like I said, the only problem is that if you try to start using it in scenarios where it's not really relevant, okay? All right, so calculate the concentration of sodium benzoate that must be present in a 0.2 molar solution of benzoic acid to produce a pH of 4, right? So we could just go ahead and set that up the same way, right? That's what I would do, right? HA plus H2O. And then I know that 0.2 molar benzoic acid and pH of 4 means I also know that, right, this is 10 to the negative 4, and I'm looking for that. So same thing, right? I would go ahead and set this up as 6.3 times 10 to the negative 5 is equal to 10 to the negative 4th times A minus over 0.2, right? And then I would solve for my A minus concentration. Yes? Does that make sense? So Henderson-Hasselbalch is not necessarily easier, right? As long as we quickly understand the Ka expressions and how to write them and how to fill them in. But yeah, you are welcome to use it, just like that M1V1 equals M2V2, right? The only reason I discourage it is because I don't want you to get confused and use it at the wrong time. And the whole confusing what base means versus what acid means, because especially when you get to titrations, people want to do weird things with what goes into those spots. All right, thank you for listening. Be good. I will see you soon